Okay, so one powerful use of these binomial coefficients is the binomial theorem. So the binomial theorem. Okay, so let's consider the binomial x plus y cubed. So this is called a binomial because it's got two terms, x plus y cubed. Okay, now I'm going to write it out slowly. It's x plus y, x plus y, x plus y. And I'm doing it this way so that you can see that there are three terms. And from each term I can pick one of x or y, one of x or y, one of x or y, and multiply them and get a three-term sequence of x's and y's. And there are two ways to do it here, two ways to do it here, two ways to do it here, two times two product rule. That means I should get 8 sequences, and indeed I do. Okay, I'm going to get x, 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 so x, 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 plus x, x, y, x, x, y, plus x, y, x, plus x, y, y, plus, now those starting with y. Y, x, x, plus y, x, y, plus y, y, x, plus y, y, y. Okay, those are all my 8 terms corresponding to the sequences that can be produced. So there are. And what you can see here is I've produced all the 8 sequences of length 3 that contain x's and y's. And those are essentially binary sequences. You can think of x as a 1 and y as a 0. Think of x as 1 and y as 0. So these are basically the 8 binary sequences of length 3. Okay. Now if I collect together terms, you see that this is x cubed plus x squared y, okay, plus x y squared plus y cubed, except that there, the x squared y comes, there's an x squared y from here, there's an x squared y from here, and there's an x squared y from here. So there are 3 of these, and there are 3 of these, and there's 1 of each of those. And this is an example of the binomial expansion of x plus y cubed. Okay? And let's go straight to the version where I have x plus y to the nth. So I'm generalizing. So let's consider now x plus, and you should remember, you should sort of maybe recognize the coefficients 1, 3, 3, 1. Those are exactly binomial coefficients when n equals 3 and k ranges from 0, 1, 2, and 3. So we have x plus y cubed. So we go to x plus y to the n. Well, that's equal to x plus y, x plus y, x plus y, x plus y. And exactly the same fashion, I'm going to get sequences of length n. Okay, so I'm going to get sequences. So for example, the first sequence might be x, 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 all x's. So I'm going to get x, 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 all x's. So n x's. Okay, and I'll get maybe x, 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 and so on, x, y. Okay, so I'll get a bunch of sequences. How many sequences? Well, I get 2 times 2 times 2 times 2, so I'm going to get 2 to the n sequences. Now, I would like to write it in this form, this more compact form. So what are my sequences? When I collect the terms together, I can either have 0 x's, 1x, 2x, 3x, 4x, and so on up to n x's. Okay, so I'm going to have, x to the 0. If I have 0 x's, then I have n y's, y to the n. Okay, plus, x to the 1, y to the n minus 1. So I'm going to have a term with 1x, and there are a bunch of those here. 1x, 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 1x. So there are a bunch of 1x terms, and then correspondingly y to the n minus 1. And there are a bunch of 2x terms, and correspondingly y to the n minus 2, and so on, x to the n, y to the 0. Okay? And each of these terms comes from the binary sequences, the sequences which have exactly 1x, the sequences which have exactly 2 x's. But if you think of the x as a 1, that's exactly the number of binary sequences with 0 1s, with 1 1s. So there's some number of these, some number of these, some number of these, and so on. Okay, and here I'm going to have the number of binary sequences with 0 1s or 0 x's. So that should be n choose 0. And the number of binary sequences with 1 1 or 1x, that's going to be n choose 1 of those. N choose 1 of those sequences. And the number of sequences with 2 1s, so this is going to be n choose 2 of those. And so on up to the number of binary sequences with n 1s and then correspondingly 0 zeros, or n x's and 0 y's. So n choose n. Okay? So if I add all this up and we use our fancy summation notation, we have the sum from I equals 0 to n. I goes from 0, 1, 2 up to n of n choose I, x to the I, y to the n minus I. See, x to the I, y to the n minus I. Okay, so when 1, you have x to the 1, y to the n minus 1, x to the 2, y to the n minus 2. So this sum is exactly this. Okay? And that's the binomial theorem, derived using a counting argument where we count all the possible sequences of x's and y's of length n, okay, and equate those to various, monomials. Okay, and so that's the binomial theorem, derived using counting. You've probably seen this in calculus. You've probably seen this all over the place. You can also prove this by induction, by the way. So, so let's summarize. X plus y to the n. This is the binomial theorem. Okay, and if you don't like the counting derivation, well, prove it by induction. Prove by induction. For the brave. But it's not so hard. But, induction is that powerful. You can prove all kinds of things, including the binomial theorem, which we derived by counting. But as an application of the binomial theorem, consider the square root of x plus 2x raised to the power 10. So exercise. Okay, and this is solved on the slide. It's also solved in the text. Okay, so when you expand this guy, you're going to have a bunch of terms. For example, the first term is this guy, square root of x raised to the power 10. So you can treat this as x. You can treat this as y. So you'll have, you'll have 10 choose 0, square root of x to the 0 times 2x to the 10 plus 10 choose 1, square root of x to the 1 times 2x to the 9 plus and so on. So you have all the binomial terms. Okay, and the question is, when you look at each term, one of these terms will have x raised to the power 7. So you'll have x raised to the power 7 with some coefficient. What's that coefficient? What is this coefficient? What is this coefficient of x to the 7? Okay, so that's just a little challenge for you to do. I'll tell you the answer. So let me tell you the answer. It is 3360. So answer 3360 is the coefficient of x to the 7. If you can now get that by applying the binomial theorem, then you've sort of understood one of these applications of the binomial theorem. Okay, so we studied counting. Okay, we studied basic rules of counting, the sum and product rule, very important. You can always come down to the basic product and sum rules and then use those with build-up counting to pretty much count anything. You get spectacular results if you learn how to count using one-to-one correspondences, because then we have, we've counted certain things like, the binomial, the binary strings with k1s. Okay, so these binomial coefficients, the number of ways to choose subsets. Okay, and since we've counted certain things, now if you can relate other things to the things we know how to count with this one-to-one correspondence approach, okay, this bijection approach, then it's very powerful for saving a lot of effort and giving very quick and slick arguments, okay, for counting various kinds of objects. But it requires a little bit of creativity. When in doubt, sum and product rule, build up counting. Okay, and lastly, we talked about the binomial theorem. We derived it from counting, and the way counting enters into computer science is that when we try to run algorithms, especially brute force kind of algorithms that try every possible way of doing something. If you want to know how long your algorithm is going to take before you run it and wait for 10,000 hours, you need to count the number of ways of doing that thing that the algorithm is going to do. Okay? So counting is very important on its own, and it's also very important for sort of understanding how algorithms are going to run, especially brute force algorithms. So until next time, we'll develop more advanced counting tools. Okay, ciao!